charge, but I didn't know because I'm colorblind, so it was red or green.
Oh, I see.
It's like a light, no?
You're charging it.
Yeah.
Okay, so welcome back, everybody. It's great to see so many people after the conference dinner. Due to our speaker. So it's a great pleasure to have Xiao-Gang Wen here from MIT, who will speak about gapped SPT SSB phases for systems with non-invertible symmetry.
Yeah, thank you. Thank you. I'm really glad to participate in this meeting. You know, it's wonderful to see one topic from so many different angles. It's very inspiring for me. Today I'm going to talk about this gapped phase for the system with non-invertible symmetry. So the issue is that we know that when the symmetry is described by a group, we know how to classify different symmetry breaking phase, basically given by the subgroup of this symmetry group. But the more tricky, actually, is really given by this conjugated class of the subgroup, if you be more careful. And also, we know that this subgroup classification is not complete. There's some additional gapped phase, have so-called SPT order, symmetry product topology order, but which are described by the cohomology of this unbroken symmetry group. But then the question naturally arises, that is, when you have a non-invertible symmetry, what is the corresponding gapped phase? What is the corresponding symmetry breaking pattern? What is the corresponding SPT states? Because in that case, we don't have a group, we don't have a subgroup, so it seems we have to have a different setup. So here we are going to use this holographic theory for the symmetry to look at this problem. And I just learned that here, that this holographic theory have very long history. And so Nati in his paper in 1996 already mentioned that when he discussed some symmetry on the brain, he already mentioned that like every global symmetry on the brain, this is a gauge symmetry in space-time. Certainly here, the brain means a boundary, space-time means a bulk. And this is even before the ADF-CFT revolution. So there we know that the group-like symmetry on the boundary, CFT, and the gauge theory in the ADS bulk have this one-to-one correspondence. That became a very popular theory, this holographic theory for the symmetry. So from that aspect, this more recent progress are really applying this holographic picture to non-invertible symmetry. And actually for non-invertible symmetry, we don't know exactly what it is. So actually this holographic theory became a definition or defining theory for non-invertible symmetry. So we understand non-invertible symmetry through this holographic theory. That became more convenient. So our encounter with this holographic theory, actually it's a detour. We studied the gravitational anomaly at first. But certainly here, the gravitational anomaly is not the usual gravitational anomaly defined in field theory. We define that as an abstraction to have a lattice UV completion. So that is our definition for gravitational anomaly. And then we ask the following question, for anomaly-free theory, means for the theory which have a lattice UV regulation, does this theory have a hidden gravitational anomaly? We want to understand this hidden gravitational anomaly because if they do have a hidden gravitational anomaly, maybe the low energy dynamics constrained by this hidden gravitational anomaly. And so the proposal is that when we have this anomaly-free theory, then we can see whether they can be equivalent to this decomposed form. Have this boundary, have bulk, have another anomalous theory. So it have this decomposition, then we say that the theory have a hidden gravitational anomaly. Then a few years later, realize that actually the gravitational anomaly and the symmetry is the same thing. So therefore, this picture really became a picture for the symmetry. So basically, trying to find the hidden gravitational anomaly became trying to find the hidden symmetry. So that's actually the same thing. So more precisely, the statement is following. the slogan is that the symmetry is described by topological order in one higher dimension. But how can that happen? Basically, is that the boundary of the topological order exactly simulate a symmetric system. What that really means is the following. When you have a symmetry, there's many symmetric systems. But when you're given topological order, there are also many boundaries. So there's a one-to-one correspondence between the boundary of topological order and the symmetric system, such that the low energy spectrum of a topological order boundary is identical to the low energy spectrum of the symmetric system if you restrict to symmetric sub-Hilbert space, And so there's then the two spectrum exactly match. So in that sense, it's some kind of exact simulation. So in this sense, the symmetry are described by topological order. So, but however, to be more precise, actually, this bulk topology only describe this so-called holographic equivalent class of the symmetry. So many different symmetry actually are equivalent using this description. If I want to have a more refined description, how to distinguish different symmetry within one hollow equivalent class, then I need to add more information. And this more information happens to be the boundary of this decomposition. And but this boundary is a fusion higher category in higher dimension. And therefore, the generalized symmetry, say in D power 1 dimension, is described by the fusion N category. Okay. And this fusion N category actually describing the excitation on this top gap the boundary, and so those excitation on the top boundary actually physically correspond to the symmetry defect, the domain wall in the symmetry breaking phase. So those are the excitation described by this R defect. So it's a DEF means really describe symmetry defect. And also, which is important for this talk, is that the gap of the boundary actually is induced by the condensation of some anions inside the bulk. So there are some collection of anions which have a trivial statistics and a trivial mutual statistics, so that they can condensing together. The maximum set of this anion from so-called Lagrangian algebra, and their condensation would produce the gap of the boundary. In the symmetry context, it turns out to be that the Lagrangian algebra, this anion which is condensing together to forming this boundary of a symmetry defect, and this condensed algebra happen to form by the anions which carry symmetry charge. So it's a very nice duality. So the anion which is condensing happen to be the correspond to symmetry charge, and then their gap the boundary have an excitation which describing the symmetry defect. So that's became this picture of using the fusion category to describe all kind of symmetry, and this holographic equivalence really means that if two fusion category have a same center, then this same bulk, then these two fusion category would describe a hollow equivalent symmetry. The hollow equivalent symmetry have a property that they kind of equivalent in the sense that they have same phase diagram, same CFT, in some sense they are really very close. But however, the labeling, the name is different. In modern language, that the hollow equivalent symmetry really related by the duality. When you have a model with a symmetry, then the dual model would have this hollow equivalent symmetry. And the dual model are identical if you restrict yourself to the symmetric sub-Hilbert space. So if, in a sense, if you restrict yourself to symmetric sub-Hilbert space, all those duality, hollow equivalence, they are all really identical. Yeah, so that's the meaning of duality. Okay, so using this picture, this holograph picture, then we can address some very common question, but now we'll apply for non-invertible symmetry. For example, what is SPD states? What is symmetry enriched topological order? So in this 2020 paper, we kind of study this problem. It's for SPD states, it's easier to state. So the result is following that the SPD phase for anomaly-free symmetry, including non-invertible symmetry, is really classified by the automorphism of this bulk topology order. So that's basically the relation. But however, not every automorphism. It has to be automorphism which keeps symmetry unchanged. But what do you mean by keep symmetry unchanged? Then it's related to this Lagrangian condensed algebra, which are formed by symmetry charge, whose condensation gives you this boundary fusion category describe the symmetry defect. So by keeping symmetry unchanged means that this automorphism alpha do not act on the charge in this condensed algebra. So the fix of those onions inside the condensed algebra. So that kind of automorphism is a subset of the automorphism. And the claim that this subset of automorphism somehow classify or describe SPD phase. So that's one result. And the motivation to see this result is the following. Usually there's automorphism in the bulk topology order correspond to this transparent or invertible domain wall. So there's an actual domain wall which are transparent invertible domain wall and which is describing automorphism. But this domain wall can be viewed as a formed by the condensation of onions. But the condensing onion, it can form many things, including symmetry breaking states. Because we require this domain wall to be invertible or transparent, so those onions can only form these SPD states on the domain wall. Then that gives rise to invertible domain wall, and that corresponds to automorphism. Then you can see that from this point of view, it's very natural that automorphism and SPD are kind of at least very, very closely related. And but certainly we can also, So here let me try to explain a little bit of the physics, some physical picture of condensed algebra. Condensed algebra have been mentioned many times in this conference from all different angles. So how to describe this condensed algebra? So let's consider a gapped boundary of this bulk topology order. And here we consider the 1+1 dimensional boundary of 2+1 dimensional bulk. Then to characterize this boundary, what we do is we insert the onion word line. This is space-time picture. Insert onion word line in this picture, and examine Guangxi generality. And then the Guangxi generality just given by some non-negative integer. AI is non-negative integer. And indexed by the onion we insert in the bulk. But sometimes when you insert the onion in the bulk, the boundary is not in the ground state because the boundary, this onion do not condense on the boundary, so boundary cannot absorb this onion. So boundary always in the excited state. I have infinity degeneracy. In this case, we say AI equal to 0 because there are no ground states. It's only excited, no ground states. And so from this physical point of view, you can really see that for every boundary is characterized by a set of non-negative integer. And this non-negative integer is an important part of condensed algebra. It can be written as a direct sum of onions, and which describes the vector space of a condensed algebra. It turns out that for simple case, this description is pretty powerful. Usually they uniquely specify the condensed algebra. So this gave us a physicist a kind of a lazy way to study condensed algebra, not study algebra, just study the vector space. Anyway, so here we just using this simple version of a simple point of view of condensed algebra, just doing this direct sum of onion. Okay, so using this condensed algebra point of view, there is a more general result. That is the gapped boundary. When a given topology order, they have many different boundary phases. Then these gapped boundary phases are classified by the condensed algebra. Lagrangian condensed algebra. So therefore, if you have a classification or computation of a Lagrangian condensed algebra, you actually classify the gapped phase of a certain symmetry, including non-invertible symmetry. So this is actually the calculation we are going to do. And so actually, I don't have time to really explain this calculation. actually there is some kind of pretty definite calculation from the bulk topology order to compute always condensed algebra, but certainly this is a simple-minded version for condensed algebra. So we can write the computer code and just plug in the group, then you can get plug in the topological order in one higher dimension, then you can get all kinds of condensed algebra. And then you compare with some kind of known result. So today I just try to present some result, those computation. And so let's consider this gapped phase for this 1 plus 1D system with A4 symmetry, Why do A4? Because S3 and D8 has been discussed in this meeting, so I pick another group. So for A4, it have I don't know how many, I forgot. It's well, have some number. I should write it down. Have some number of onions, and so this D is a quantum dimension of this onion. So okay, I go back a little bit. So this A4 symmetry is described by this from fusion category. Described this VEC A4 fusion category, whose bulk is A4 quantum double. So it's a modular tensor category, and this modular tensor category 2 plus 1D topology order have those onions labeled by 1, U, V, X, Y, Z, etc. So this onion have this kind of quantum dimension. They are all integer and have this topological spin. It's 1/2 or 1/3, things like that. So those are kind of bulk topology order. And so it turns out that this 1 UVX, this 4 onion correspond to the A4 charge. Because this A4 quantum double in 2 plus dimension basically is A4 gauge theory. A4 gauge theory have this A4 charge. So that is 1 UVX. And this 1 GHZ is a A4 symmetry defect. It's basically gauge flux. It's a gauge flux of A4 gauge theory. So remember that the A4 symmetry is described by this VEC A4. So they are coming from the condensation of this A4 charge. So indeed, we compute the condensed algebra for the A4 quantum double. And we find that there's 7 Lagrangian condensed algebra. So those are 7. And the one in blue is also condensed algebra, which you can see that only formed by symmetry charge. And this condensed algebra, whose condensation would give rise to the boundary described by VEC A4. So that corresponds to this A4 symmetry. So that's this picture. Yeah.
So if it can be that if there are 2 algebras that have the same objects, but they differ from the multiplication map. So you would, it can be that just classifying the objects in the algebra, you're missing some splitting of the phases.
So this is, I don't know what you call it, but I think I mean that in this simple-minded description, we are missing data. We have missing data. Yeah, sometimes this one derived sum onion may describe 2 different condensed algebra. So we have this, potentially we have that. So actually we have to check. We don't miss anything. So for A4, so this is because I don't have a code to computing this algebra, so it's hard to do that. But as a physicist, we can, there's other way. Because this is A4 symmetry. So I know the symmetry breaking patterns, this country class subgroup, SPT group homology. We find, yeah, we do get only 7 states. Okay. So this is important. We have to do this check, make sure we don't miss anything. At least for the group we encountered, they all pass this check. So this distribution is okay. But certainly, we hope to have another program to really computing this condensed algebra. But that's corresponding computing the F symbol in the MTC. Computing F symbol is so at the moment it's very hard. So right now the program we write is at the level of modular data. We avoid using F symbol. Try to say within using this framework how far we can go basically. Yeah, for simple case it looks pretty okay. And also there's an automorphism. Automorphism is very important. So here we also compute automorphism again in a very simple-minded setting. because the bulk topological order are described by modular data. So when you look at the modular data, the automorphism simply is an onion permutation which keep ST matrix invariant. So using that automorphism. So that automorphism group happened to be this, for this A4 symmetry happened to be S3 times Z2 times Z2, generated by this kind of permutation of onions. Okay. And then use automorphism group, we can divide this 7 Lagrangian condenser algebra into 3 orbit of action of automorphism. So which are labeled, the first index just an index for this orbit. The second index is describing the Lagrangian condenser algebra inside each orbit. So we have a 3 orbit, so that's why we use this double index to label those condenser algebra. So this we can obtain from this computing code. And then how to view this physically. And so because we have a 3 orbit, that means for this A4 quantum double is actually describe this hollow equivalent class of a symmetry, and this equivalent class have 3 symmetries. You have a 3 orbit, so the 3 symmetry. The A4 symmetry is a wonderful symmetry. That's a VEC A4. Certainly rep A4 is another symmetry. Then there's a third symmetry, which is I don't know how to name this because there's no common name. So it's just this A4 quantum double whose boundary induced by this A11 condensable algebra. So A11 is this condenser algebra. So this one also Lagrangian condenser algebra. You can condensing that produce another symmetry. This symmetry turns out to be anomalous. So in a sense, always a gap state are gapped.
So is it possible the third one is just Z2 times Z2 with anomaly? No? It's like obtained by gauging a Z2. From
maybe, yeah, I haven't really looked into that there. Yeah, Z2 cross Z2 is anomaly.
It's anomaly, yes.
So Z2 cross Z2 with mixed anomaly.
Between the two Z2s. I think you get it from gauging a Z2 inside a Z4. I mean, we can discuss.
Yeah. You have to look at it. Okay, yeah. Okay. And so therefore this so then this A4 symmetry is just taking this back A4. Okay. And then so we have a 7 gap fix. A4 symmetry have a 7 gap fix. That's it. Then we also have a more detailed description. How to describe this gap fix. One way to describe those gap fix using their ground state degeneracy. And the ground degeneracy turns out to be the kind of inner product between the condenser algebra and also the condenser algebra formed by symmetry charge, which are producing symmetry. And so then we find using ground degeneracy, this 7 gap phase can be written as a 2 plus 2 plus 1 plus 1 plus 1. The subscript is a ground state degeneracy. There are 2 states with a unique ground state. That is a 2, 1. So those are usually called SPD phase. There's no symmetry breaking. And other with non-trivial ground state degeneracy, they are kind of symmetry breaking phase. And this match the group chronology calculation. And then for the okay. But however, using this ground state degeneracy is not best way to separate, to describe a gap phase. Because many times the 2 different symmetry breaking patterns produce same ground state degeneracy. So symmetry breaking pattern seems is a better way to describe it. But how do you define symmetry breaking pattern in general from using the holographic picture? Then here is we use automorphism. Basically, the automorphism, which is fixing this A4 charge, is we call the symmetry automorphism. And then this condenser algebra connected by symmetry automorphism form this we call the symmetry breaking class. So we say each class have same symmetry breaking pattern, and the different class have a different symmetry breaking pattern. So therefore, we can group this 7 gap phase into this symmetry SSB class. And so that's the grouping. And so we say that the different class have different symmetry breaking pattern, and the gap phase within the same class differ by SPT order by definition, because these phase differ by automorphism. So we say that difference is SPT order. So that's how we organize these states. And you can do this for the rep A4 symmetry. The result is that for rep A4 symmetry, we also have a SPT states, because we have a ground state determinant 1, but they have two class, two in the same class with the ground state determinant 1. So rep A4 also have a two SPT state, a trivial one or non-trivial one. An interesting situation happen when you have a S3 times Z3 symmetry. Well, this is not interesting. The interesting one is because time, let me just skip to here. It's a rep S3 times Z3 symmetry. Okay. So again, this is a gap phase. You have a time gap phase. Okay. Now what is fun is that there are two gap phases with a unique ground state, but they are not connected by automorphism. So this is a surprise, and because we thought that the gap phase with unique ground states, their SPT phase, they should be related by some kind of automorphism, but actually this is a counterexample. They are not related by automorphism. So from our definition, we should say we have a two gap phase with unique ground state, but they have a different symmetry breaking pattern. And so we're kind of debating on this. Should we do using this kind of way to organize it, or maybe we should simply define the gap phase with unique ground state as SPT. They are, after some thought, I thought using this automorphism to define SPT maybe is a better way to organize things. Actually, there's a physical implication. We kind of suggest that although these two phases with unique ground states, we kind of suggest that they are locally distinguishable. But we have not really get the mathematics to really show that. But from some thinking, if our thinking is right, they suggest they are locally distinguishable. The SPT phase have another character that in the bulk, they are indistinguishable. They can only be distinguished at the boundary. So using automorphism, you can naturally have this result. The phase differ by automorphism are indistinguishable from the bulk. Only distinction is at the boundary. But here, these two phases are not connected by automorphism, suggesting maybe they are distinguishable at the bulk. Actually, we look at the symmetry breaking pattern a little more carefully. Indeed, for non-invertible symmetry, even with unique ground state, you could have a different symmetry breaking pattern. And one hint is that maybe some symmetry actions became zero. For invertible symmetry, for symmetry unbroken state, the action of symmetry just give you a phase factor. For non-invertible symmetry, they are not phase factor. They can be some numbers, integer. And the pyramid can be zero, And so maybe this is a reason. So basically, it's just a way. It's just maybe. Yeah, we try to say maybe this is a better way or more reasonable way to organizing different gap phases for non-invertible symmetry. And this phenomenon happened for the rep D8. Rep D8 have three gap phase with unique ground states, which is what's called three different SPT states. But they are not connected by automorphism, and which fix the symmetry charge. And the example we have is here. But in other cases, like rep A4, these two phases are connected by automorphism. These are really SPT phase. Okay, thank you. Yeah, that's my part.
It was nice talk. Other questions?
So if you take the double A4, if you condense the A11, what's the fusion category you get? The fusion category you get?
I don't know. Yeah. It's a very important. Maybe it's Z2. Yeah.
One question is, it's some non-invertible symmetry.
No, this one is non-invertible.
It's non-invertible.
It's non-invertible. Yeah. Yeah.
Did you look at the, so you've done the analysis for the gapped phases. Have you also looked at the, for the A4, the higher, the not maximal,
We have the computation have that. So there's a lot of gapless phase.
do you have?
Again, we can organize in a similar way. There are some gapless phases that connect by automorphism. Then we say, oh, those two gapless phases are different by SPD order. And some they are not connected by the SPD phase. And some gapless phases actually have this actual ground state degeneracy. So we say that's a symmetry breaking gapless phase, and there's a SPD gapless phase. Actually, they're all there in this framework. I only present the gap story because this our simple-minded calculation of conventional algebra, which is even more unreliable for gapless phase. Yeah, so at least for gap phase, the condition is stronger, so it's more likely to be right. The gap phase, we may have a fake solution that there's a concern.
But is there, for example, for the A4 case, some of the symmetry versions of that are the IGSPT, so intrinsically gap?
They're all there. I can send you some kind of table.
Yeah, so like we organize them in a Hasse diagram. So
I need to understand that. So they can organize into this nice way. Yes.
Okay. Any other questions? So.
Thank you for the talk. If I got the point of what you said at the end, let me just contextualize it in Rep D8. So there's many papers now that say there's 3 Rep D8 SPGs, but you would want to say some of those are Rep D8 SBs, right?
Yes.
Okay, and the definition you're proposing is to treat this anion automorphism in the bulk as being superior to the ground state degeneracy.
So actually,
I want to ask my question now. Is there a physical reason without using the bulk to give such importance to the anion automorphism from the physical 1+1D theory? Because ground state degeneracy seems very physical. I can see it without using the bulk.
Yeah, that's you're totally right. And so the deciding factor for us is the following. Using unique ground state to define SPT is very reasonable. Just that remark here. And but however, we also have SPT for symmetry breaking phase. Sometimes we have 2 different symmetry breaking phases, only differ by some kind of SPT order. If you're using the ground state unique ground state to define SPT, then generalizing that, applying this definition to symmetry breaking states will be very difficult. They don't organize in the same way. If you're using automorphism, then it's very natural because automorphism also act on the symmetry breaking states at equal footing, in the same way. So it's very easy to see whether 2 different symmetry breaking states are different by automorphism or not. But to identify 2 symmetry breaking states, are they different by SPD states? If you define SPD state using unique ground state, there's difficulty. We could not. So if you're using ground state degeneracy, using unique ground state to define SPD states, then that SPD concept cannot be applied to symmetry breaking states. At least we don't know how to apply that. If I define SPD using automorphism, then it's very natural to apply to symmetry breaking state, to gapless states. So it's a very natural. But what I'm suggesting actually, I feel it's more important that if this automorphism is a good organization, it really means that we have 2 different gapped phases with unique ground state. They are distinguishable from bulk measurement. But that requires some really serious calculation. I don't know in which bulk measurement they are different, but at least there's a suggestion, there's a possibility they are distinct from bulk. And so at the moment, it's just initial, just at the beginning start of this project, but the suggestion that maybe there's a bulk distinguishable. Then if that's really true, then this organization will be very reasonable. But we have not proved the bulk distinguishable, so at the moment it's just conjecture.
Any fun?
Christian. So maybe a follow-up question to Sal's question. So if I understand correctly, if you want to interpret this identification at the 1+1 dimensional level, it should correspond to generalized gauging. Is that correct? That's what.
Yeah, maybe I don't know. It's example the generalized gauging is
I mean, from the examples you wrote, I think that is. And this fusion categories that you listed before, this A4, rep A4, and so on, they're just two categories that are right gauging. Z2 times Z2 would not be possible.
I already corrected myself.
Okay, you did. Okay.
Non-invertible.
Wow. Yeah. So first of all, total quantum dimension have to be the same. Yeah.
Yeah.
I already said.
Yeah. I didn't hear it. Yeah, I didn't finish. Oh, you want to say on the number? No. So I think the mathematical framework to understand this orbital structure is this broad Picard group point structure.
Okay.
Have you looked into that?
No, I heard of this Picard group, but I just heard this name. My collaborator write about it.
We can talk about it afterwards.
Great. Any other questions?
It's actually related to Yifan, essentially. So I think for invertible symmetries, SPT is formed also over a group, no? So that might be related to the fact that you have this automorphism that exchange in them.
I see.
But when the symmetry is non-invertible, there is no group structure because there is no stacking, no?
Yeah, there's no standpoint.
That's why you don't see this anymore.
Yeah. So actually, SPT have another important thing as an invertible and stacking, but for non-invertibility, we don't have that. So here, this non-invertibility really became the automorphic in the bulk. In that sense, there's some invertibility. It's very different from stacking invertibility. Yeah. Thank you.
Okay, I think we should close. Let's thank Xiao-Gang again for a nice talk.